Now, an isomer is a molecule with its atoms representing themselves in different ways in 3D space. Now, that may sound complicated, but it's not all that bad. And I can show you how it's not that bad with my attention grabber of the day. You get to draw your own house. So, you'll notice that everyone has a piece of paper with this drawing on it. Now, on that drawing, I want you to design your dream house within my limits of 1 door, 6 windows, 4 stepping stones, 1 potting plant, 1 chimney, no more, no less. Make sure you have it all, and go. Okay, so here I've got everybody's drawings. I don't know if I can get these to stand without falling, but I want you to notice that even though we all had the same 1 door, the same 6 windows, the same potting plant, the same chimney, you'll notice that not a single one of these houses is the same. But that seems to make sense, right? They don't have to be the same even though we use the same products. Well, that's the same as an isomer. See, a chemical formula is just a recipe, right? Yeah, H2O or CH4. But we can represent those differently in 3D space, much like we've done here. So I'm going to go ahead and put that in a more chemical term and change this house into molecules. All right, class, thank you for your patience while I erased the board and wrote up these seemingly difficult chemicals that we can change to isomers. So first I want to start with the most simple of isomers, because I think I can do that. And then we're going to get on to the more difficult isomers that I think I'm going to need your help with. So up here, you'll see that we have our N-pentane. Remember from nomenclature a few weeks back, pent, 5, pentane, we have 5 different carbon atoms. Now you can see that this carbon here can kind of slide wherever it wants, right? It still has that single bond. So we can take this N-pentane and move this C to here, and you're going to see that it's now neopentane. It's still 5 carbons, so nothing changed as a formula or a recipe, but how it's shaped in 3D space has definitely changed. And this will present itself in different properties, which we'll get to later. Now, it's important to realize that if we moved it to any other side, if we were to continue down, you might think that we could do that, but we can't. Because if we move this one here, it's the same as if it had been here, just flipped. So we can't do that. So now we're going to get into more difficult isomers. We're going to look about groups and smaller groups. And I'm going to start with this one here. Alicia, do you see a group that we could take versus 1 atom that we could move? Absolutely. I think that we could take this group. But there's going to be a little bit of a problem, this extra H. So why don't we think a little bit smaller? That's right. What if we did just this vertical group and we switched it with, say, the oxygen, 2 bonds for 2 bonds? We would then have something that looked like this. So we took this column and we replaced it with this O. They just swapped. Do we still have the same formula, Alicia? Yes, we do. Is it represented differently in 3D space? Absolutely. Let's go with this one, and the hardest one, I think. This is more of a group versus a column. David, what do you think we could do here? Oh, you fell right into my trap. We can't do just that column. Because much like with this C here, if we replace this column with this column, we didn't change anything. We just kept it the same. So we need to look for a group. David, what do you think we could do for a group? Absolutely, we could do this whole group. We could do that vertical plus that H. And again, with this single bond, replace it with any other single bond. Right, so we might be able to say take this group and replace it with the H. Now just for time, I'm not going to draw all the hydrogens, but this group would come down to be C, H, H, H. And this hydrogen here would go there. So this hydrogen went here, this group with there. Of course, we would fill in the H's elsewhere to make that look the same. This is definitely the most difficult isomer where we're moving a group. And it can get harder and harder by moving groups of groups of groups, right? We can move this group on top of that H and switch those. We can do a lot of things. But so long as our electron domains are satisfied and full, we still have isomers. Class, thank you very, very much for participating in that and helping me figure this out. Now, I want you to see if you can do this on your own. So you're going to see that I'm going to hand out this worksheet, and it has 8 different molecules that I want you to find as many of the isomers as you can. This will not be graded, but more of a completion score. And I want to see tomorrow if you take this home and you're able to find as many as I can.